Before quantum theory emerged as a mathematical framework or a physical revolution, it existed in a far quieter place, the philosophical imagination of a man who believed that nature was governed by deep, immutable truths. To understand the first keynote, the philosophical roots of scientific curiosity, we must step into a world where science and philosophy were not separate domains, but two expressions of the same human desire to understand reality. This was the intellectual climate that shaped Max Planck's. Long before he became associated with equations, constants, and revolutions in physics. In the 19th century, German intellectual life was profoundly shaped by philosophy. Thinkers such as Kant, Hegel, and Schopenhauer were not abstract figures confined to philosophy departments. Their ideas permeated education, culture, and science. For many scholars of the time, philosophy was not speculation detached from reality, but a disciplined attempt to uncover universal principles underlying existence. Science, in this worldview, was a continuation of philosophy by empirical means. Young minds entering physics were expected to think not only in terms of experiments and formulas, but also in terms of meaning, order, and truth. Planck grew up immersed in this tradition. From an early age, he was taught that the universe was rational, structured, and governed by laws that existed independently of human observation. This belief was not merely academic, it carried moral and almost spiritual weight. Nature in this view was not chaotic or arbitrary. It was lawful, and those laws were waiting to be discovered by careful reasoning and disciplined inquiry. Scientific curiosity, therefore, was not driven by novelty or disruption, but by reverence for order. This philosophical stance deeply influenced Planck's understanding of science. He did not see the role of a scientist as an inventor of models, but as a discoverer of truths that already existed. Laws of nature were not human constructs to be revised at will, they were eternal realities. The task of physics was to uncover them as accurately as possible. This conviction placed him firmly in opposition to more pragmatic or instrumentalist approaches to science, which treated theories merely as tools for prediction rather than descriptions of reality. At the heart of this worldview was determinism. Classical physics had taught generations of scientists that if one knew the initial conditions of a system precisely enough, its future could be predicted with certainty. This idea resonated deeply with philosophical notions of causality and necessity. Nothing happened without a reason, nothing was fundamentally random. For someone like Planck, abandoning determinism was not just a scientific shift, but a philosophical and even existential threat. Scientific curiosity, in this philosophical sense, was not about asking, what works, but what is true. This distinction is crucial. Many scientists are motivated by usefulness, by results that allow technology or prediction. Planck's curiosity was of a different kind. He was motivated by the conviction that the universe made sense, and that human reason, when properly applied, could grasp that sense. This is why he was drawn to theoretical physics rather than experimental tinkering. Theory to him was closer to philosophy, a structured language capable of expressing universal truths. This mindset also explains his attraction to thermodynamics, particularly the concept of entropy. Entropy was not just a measure of disorder, it was a profound statement about the direction of time and the limits of physical processes. For Planck, the laws of thermodynamics had an almost metaphysical status. He believed they were absolute, not statistical approximations arising from ignorance. This belief set him apart from contemporaries who were beginning to accept probabilistic interpretations of physical laws. The philosophical roots of scientific curiosity also shaped how Planck viewed uncertainty and ignorance. He did not believe that randomness was a fundamental feature of nature. Instead, uncertainty reflected limitations in human knowledge or measurement. Nature itself, he believed, was exact and precise. This belief would later place him in a deeply uncomfortable position when quantum theory began to suggest that uncertainty might be intrinsic to reality itself. It is important to understand that this philosophical background did not make Planck rigid or closed-minded. On the contrary, it gave him an unusually strong sense of intellectual responsibility. If nature contradicted theory, then theory had to be revised, not casually, but reluctantly and carefully. Philosophy taught him humility before truth. He did not chase bold ideas for their own sake. He followed evidence, even when it led him away from his deepest convictions. Scientific curiosity rooted in philosophy is slower, more cautious, and often more painful than curiosity driven by ambition or competition. It requires patience and a willingness to endure internal conflict. Planck's later writings reveal how deeply troubled he was by the implications of his own work. This inner struggle did not come from confusion, but from clarity. He understood exactly what was at stake philosophically, and that understanding made every step forward heavier. In this sense, the birth of quantum theory cannot be separated from the philosophical character of its reluctant founder. The revolutionary consequences of quantization were not born from a desire to overthrow classical physics, but from a philosophical commitment to truth. When Planck introduced the idea that energy might be exchanged in discrete units, he did so not because it aligned with his worldview, but because reality demanded it. The philosophical roots of scientific curiosity also explain why Planck remained skeptical of many later interpretations of quantum mechanics. Even as younger physicists embraced indeterminacy and probability as fundamental, he held on to the belief that a deeper, deterministic layer of reality might yet be discovered. This was not stubbornness. It was fidelity to a philosophical ideal that had guided his entire intellectual life. To understand this keynote is to recognize that quantum theory did not emerge from chaos or rebellion, but from order, discipline, and philosophical seriousness. The very ideas that quantum theory would later challenge, determinism, continuity, absolute law, were the same ideas that motivated its first step into existence. This paradox is not accidental. It reveals something profound about how science advances not by rejecting philosophy, but by being shaped by it. In the end, the philosophical roots of scientific curiosity are not a historical footnote. They are the foundation of one of the greatest transformations in human thought. A man who believed deeply in eternal laws discovered a universe where those laws operated in ways no one had imagined. Yet he did not abandon his philosophical integrity. Instead, he demonstrated that true curiosity is not about defending beliefs, but about serving truth, even when that truth reshapes the very philosophy that inspired the search. The same philosophical roots that shaped Max Planck's early curiosity also defined how he reacted emotionally and intellectually when those roots began to tremble. Scientific curiosity grounded in philosophy does not simply seek answers. It seeks coherence between what is known, what is believed, and what is meaningful. This is why Planck's journey is so psychologically rich. His curiosity was not neutral. It was charged with values, with a sense of duty to truth, and with a profound respect for the idea that nature itself was rational. From his earliest academic years, Planck viewed the pursuit of science almost as a moral vocation. Knowledge was not something to be manipulated for convenience, nor were theories provisional stories to be discarded lightly. He believed that the universe had an objective structure independent of human observers. This belief gave him confidence, but it also imposed a heavy burden. If nature was objectively lawful, then any contradiction between theory and experiment was not an invitation to invent arbitrary explanations, but a demand for deeper understanding. This attitude distinguished him sharply from many of his contemporaries. By the late 19th century, a growing number of physicists were becoming comfortable with pragmatic approaches. If a theory predicted results correctly, that was often considered sufficient, even if its conceptual foundations were shaky. Planck found this attitude deeply unsatisfying. For him, prediction without understanding was incomplete. He wanted theories that were not only effective, but true. This distinction matters because it explains why Planck struggled so intensely with probabilistic thinking. Statistical methods were becoming increasingly popular, especially in thermodynamics and kinetic theory. Many physicists accepted probability as a practical necessity. Systems with too many particles to track individually could only be described statistically. Planck, however, resisted the idea that probability reflected anything fundamental about nature. To him, probability was a confession of ignorance, not a property of reality. His curiosity was therefore directed not toward averages or likelihoods, but toward absolutes. He wanted to know what must be the case, not merely what usually happens. This philosophical orientation led him to view entropy, for example, as an exact law rather than a statistical tendency. He believed the second law of thermodynamics possessed an objective, universal validity that did not depend on human knowledge or observational limitations. This belief placed him in an increasingly isolated position as physics advanced. New experimental results were forcing scientists to confront phenomena that did not fit neatly into deterministic frameworks. Radiation, atomic spectra, and microscopic behavior all hinted at irregularities that classical laws could not explain. Many younger physicists were willing to reinterpret these anomalies as signs that nature itself might be probabilistic. Planck could not accept this easily, because it struck at the philosophical heart of his curiosity. Yet this same philosophical seriousness is what made him uniquely capable of enduring the tension between belief and evidence. A less philosophically grounded scientist might have dismissed the anomalies as experimental errors or adopted ad hoc explanations without concern for coherence. Planck did neither. He trusted experiments, but he also trusted reason. When the two conflicted, he did not rush to resolution. He allowed the conflict to exist, even when it caused deep discomfort. This is where the documentary character of his intellectual life becomes especially vivid. Letters, lectures, and later reflections reveal a man wrestling not just with equations, but with the meaning of scientific knowledge itself. He was acutely aware that accepting certain results might require abandoning ideas he had held since youth. His curiosity did not shield him from this pain, it intensified it. Philosophical curiosity, unlike purely technical curiosity, is deeply personal. It ties identity to understanding. When foundational beliefs are challenged, the challenge feels existential. Planck experienced this when he realized that classical explanations of radiation were failing. He did not celebrate this failure as an opportunity for revolution. He experienced it as a crisis. What sustained him through this crisis was not ambition or desire for recognition, but loyalty to truth. Philosophy had taught him that reality does not bend to preference. If the universe behaved in a way that contradicted cherished principles, then those principles had to be questioned. This does not mean they had to be discarded entirely, but they could no longer be treated as unquestionable. This ethical commitment to truth over comfort is one of the most important features of Planck's scientific curiosity. It explains why he described his introduction of energy quanta as an act of desperation rather than inspiration. He did not see himself as inventing a new picture of reality. He saw himself as cornered by facts. The tragedy and the greatness of his position lies in the fact that he understood the philosophical implications of what he was doing more clearly than many who followed him. He knew that discretizing energy threatened continuity, one of the most deeply embedded assumptions of classical physics and philosophy. Continuity was not just a mathematical convenience, it was a metaphysical commitment to smooth, causal evolution. To give it up, even partially, was to open the door to a radically different conception of nature. Planck hesitated at that door for as long as he could, but philosophical curiosity is not the same as philosophical conservatism. It does not exist to protect old ideas, but to seek coherence between belief and reality. When coherence breaks, curiosity demands repair, even if the repair reshapes the entire structure. Another crucial aspect of this keynote is the way Planck distinguished between understanding and explanation. He was willing to accept a formula that worked, but he was not satisfied until he understood why it worked. This is why he initially treated quantization as a formal assumption rather than a literal description of nature. He hoped that a deeper classical explanation would eventually emerge, one that preserved continuity and determinism while reproducing the same results. This hope never fully materialized, but it shaped his lifelong attitude toward quantum theory. Even as the theory expanded and succeeded, Planck remained cautious about its philosophical interpretation. He supported the mathematics, defended the empirical success, and encouraged younger scientists. But internally, he continued to believe that quantum theory was incomplete at a fundamental level. This belief is often misunderstood as resistance to progress. In reality, it reflects the depth of his philosophical curiosity. He was not opposed to new ideas, he was opposed to shallow acceptance. He wanted a worldview in which physics, philosophy, and reason formed a coherent whole. Until such coherence was restored, he regarded the quantum revolution as unfinished business. In this sense, the philosophical roots of scientific curiosity did not end once quantum theory was born. They continued to shape how Planck interpreted its meaning and limits. His curiosity never settled into complacency. Even when honored, celebrated, and recognized as a founder of a new era, he remained intellectually restless. This restlessness was not dissatisfaction with success, but fidelity to a deeper ideal. Science for him was not a collection of results, but an ongoing dialogue between human reason and the structure of reality. Philosophy was not an external commentary on this dialogue, it was its foundation. Understanding this allows us to see quantum theory not merely as a technical breakthrough, but as the outcome of a profound philosophical journey. The first keynote is not simply background context, it is the emotional and intellectual engine that drove everything that followed. Without this philosophical form of curiosity, disciplined, humble, and deeply committed to truth, the quantum revolution might never have begun, or it might have taken a very different path. Planck's legacy, therefore, is not only a constant, an equation, or a theory. It is a model of what scientific curiosity can be when it is rooted in philosophy, a curiosity that does not chase novelty, but endures uncertainty, a curiosity that does not flee contradiction, but confronts it, and a curiosity that remains loyal to truth, even when that truth transforms the very beliefs that inspired the search. By the end of the 19th century, physics stood at what many believed was the edge of completion. The great structures of classical thought appeared solid and unshakable. Newtonian mechanics explained motion from falling apples to planetary orbits. Electromagnetism unified electricity, magnetism, and light into a single elegant framework. Thermodynamics described heat energy and work with laws that seemed universal and final. To most observers, the universe looked like a perfectly wound clock, governed by continuous, deterministic laws that left little room for surprise. This confidence, however, masked a growing unease. Beneath the surface of triumphant equations and successful predictions, small but persistent inconsistencies began to appear. These inconsistencies did not announce themselves dramatically. They emerged quietly, in laboratories and calculations, as stubborn experimental results that refused to align with established theory. At first, they were treated as technical problems, minor imperfections that would surely be resolved with better measurements or refined mathematics. Few suspected that these anomalies signaled a profound crisis. Classical physics rested on several deeply held assumptions. One was continuity. Physical quantities such as energy, position, and time were believed to vary smoothly, without jumps or gaps. Another was determinisms. Given complete knowledge of a system at one moment, its future behavior could be predicted with certainty. A third was universality. The same laws applied at all scales, from everyday objects to the smallest particles, even if those particles were not yet directly observable. These assumptions were not merely practical, they were philosophical commitments inherited from centuries of scientific thought. For decades, these commitments had been rewarded with extraordinary success. Engineers built machines, astronomers predicted celestial events, and physicists refined theories with remarkable precision. This success created a powerful sense of closure. Many believed that physics had reached its mature form, and that future generations would merely polish details rather than rewrite foundations. It was within this atmosphere of confidence that the crisis of classical physics quietly unfolded. One of the first warning signs appeared in the study of heat and radiation. When objects are heated, they emit electromagnetic radiation. This radiation depends on temperature and frequency, and it can be measured with great accuracy. Experimentalists developed increasingly precise instruments to study this phenomenon, producing data that demanded theoretical explanation. Classical physics, confident in its continuity and determinism, offered predictions based on established principles. Yet these predictions led to absurd conclusions. According to classical theory, a heated object should emit ever-increasing amounts of energy at higher frequencies, implying infinite energy output. This result was not just inaccurate, it was physically impossible. Experiments showed that radiation peaked at certain frequencies and declined beyond them. The mismatch between theory and observation was undeniable. At first, physicists attempted to patch the problem. They introduced corrective assumptions, empirical formulas, and mathematical tricks designed to fit the data without abandoning classical principles. These efforts reflected a deep reluctance to question the foundations of physics. After all, the existing framework had proven its worth time and again. It seemed far more reasonable to suspect that the problem lay in incomplete modeling rather than in the core assumptions themselves. This pattern repeated across multiple areas of physics. Atomic spectra displayed discrete lines rather than continuous distributions. The behavior of electrons in metals defied classical expectations. Measurements at microscopic scales produced results that could not be reconciled with deterministic trajectories. Each anomaly, taken alone, might have been dismissed. Together, they formed a growing pattern of resistance from nature itself. The crisis of classical physics was not immediately recognized as a crisis. It unfolded gradually, as a series of frustrations rather than a single catastrophic failure. Many senior physicists continued to believe that a complete classical explanation was just around the corner. This belief was reinforced by the philosophical conviction that nature must be continuous and deterministic. To abandon these principles felt not only scientifically risky, but intellectually irresponsible. The emotional tone of this period is often misunderstood. It was not a time of excitement about revolution, but of anxiety about inconsistency. The anomalies threatened the coherence of physics as a rational enterprise. If classical laws failed in certain domains, what did that say about their universality? If energy behaved differently at microscopic scales, could the same laws truly govern all of nature? For thinkers like Max Planck, this tension was especially acute. He had been trained to believe that physical laws were absolute truths, not provisional models. The idea that foundational principles might break down under scrutiny was deeply unsettling. Yet the data could not be ignored. Experiments were becoming more reliable, not less. Precision increased, and with it, the clarity of the contradictions. The crisis was also intensified by advances in experimental technique. As instruments became more sensitive, they revealed behaviors that had previously been invisible. Classical physics had been developed primarily to describe macroscopic phenomena, objects large enough to be seen and measured directly. When attention turned to microscopic processes, the old assumptions were stretched beyond their limits. This shift exposed a crucial vulnerability in classical thinking. Determinism worked beautifully for systems with a few degrees of freedom, but it became unwieldy for systems involving countless interacting components. Continuity made sense at human scales, but it was an assumption extrapolated beyond direct experience. The crisis forced physicists to confront the possibility that their most trusted principles were approximations rather than absolutes. Importantly, this was not merely a technical problem. It was a conceptual crisis. The mathematical formalism of classical physics was elegant and powerful, but it rested on intuitive ideas about space, time, and causality. When experiments contradicted predictions, the problem was not just incorrect numbers, but incorrect concepts. Physics was being asked to explain phenomena, that did not fit the conceptual language it had developed. Some physicists responded by narrowing their focus, treating anomalies as special cases that required special explanations. Others began to suspect that a more radical change was necessary. But even among those who sensed the depth of the problem, there was hesitation. Abandoning continuity and determinism meant abandoning the very features that had made physics intelligible and philosophically satisfying. The crisis of classical physics was therefore as much psychological as it was scientific. It challenged the identity of physics as a discipline that described a predictable, orderly universe. It raised uncomfortable questions about the limits of human knowledge and the relationship between theory and reality. Could science continue to claim access to objective truth if its most trusted laws failed under certain conditions? This period also revealed the inertia of successful ideas. Classical physics did not collapse under the weight of contradiction. It resisted change precisely because it worked so well in most contexts. Its success created a bias toward preservation. New ideas were evaluated not only on empirical grounds, but on their compatibility with established philosophy. This bias slowed the recognition of crisis, but it also ensured that any eventual transformation would be deeply consequential. By the turn of the century, the signs were unmistakable. Classical physics could no longer claim universal validity without qualification. The anomalies were not disappearing, they were multiplying. Each attempt to resolve them within the classical framework introduced new complications. The structure that once appeared complete now looked strained, patched, and increasingly artificial. Yet it is crucial to understand that this crisis did not immediately destroy confidence in classical physics. Instead, it created a strange duality. Physicists continued to use classical laws successfully in many domains, even as they acknowledged their failure in others. This coexistence of success and breakdown made the crisis more complex and more difficult to resolve. The second keynote, the crisis of classical physics at the end of the 19th century, is therefore not a story of sudden collapse, but of slow erosion. It is a story of a worldview confronted by evidence it could not fully explain, and of a scientific community grappling with the limits of its own assumptions. This crisis set the stage for a transformation that would not only change physics, but alter humanity's understanding of reality itself. As the 19th century drew to a close, the crisis of classical physics deepened in ways that were not immediately visible to the public, but were painfully clear to those working at the frontiers of research. What made this crisis especially unsettling was that classical physics continued to work extremely well in everyday contexts. Bridges stood, machines functioned, planets followed their predicted paths. There was no dramatic failure that forced an immediate reckoning. Instead, physicists were confronted with a more disturbing reality. Their most trusted theories were simultaneously correct and incomplete. This duality created a unique intellectual tension. On one hand, classical physics remained indispensable. On the other, it could no longer claim to describe nature at all scales. This was not a simple matter of adding corrections or refining constants. The contradictions pointed toward something more fundamental. The assumptions underlying classical theory were being tested in regimes they were never designed to explain, and they were failing. The deeper the investigation went into microscopic phenomena, the more apparent these failures became. Classical physics assumed that matter and energy could be divided endlessly into smaller pieces, each obeying the same laws as the whole. This assumption had never been directly tested at very small scales. It was an extrapolation based on success at larger ones. When experiments began probing atomic and subatomic behavior, the extrapolation broke down. One of the most unsettling aspects of this breakdown was that it defied intuition. Classical physics had shaped not only equations, but mental pictures of reality. Objects had positions and velocities. Energy flowed smoothly. Causes preceded effects in a clear, continuous chain. These intuitions were not arbitrary. They had been reinforced by centuries of experience and success. To question them was to question the very language in which physics thought. As experimental evidence accumulated, physicists found themselves increasingly reliant on empirical formulas that worked but lacked theoretical justification. These formulas fit the data beautifully, yet could not be derived from classical principles. This situation was deeply unsatisfying. Physics had always prided itself on explanation, not just description. Now it was being forced to accept results without understanding their underlying cause. This gap between calculation and comprehension was one of the defining features of the crisis. It signaled that something was wrong at a conceptual level. Theories were no longer growing organically from principles, they were being forced into place to accommodate stubborn facts. Each such adjustment increased the sense that classical physics was being stretched beyond its natural limits. The psychological impact on the scientific community was significant. For generations, physicists had believed they were uncovering the final structure of natural law. Now they were confronted with the possibility that their achievements, however impressive, rested on assumptions that might not be universally valid. This realization was not greeted with enthusiasm. It was met with resistance, skepticism, and in some cases denial. For deeply principled thinkers like Max Planck, the crisis posed a profound dilemma. He was not inclined to discard classical physics lightly. To him, its laws were not merely useful approximations, they were expressions of an objective order in nature. Yet the experimental evidence was relentless. It did not attack classical physics at its strongest points, but at its boundaries, where intuition was weakest and certainty less secure. This made the crisis particularly difficult to resolve. There was no single experiment that disproved classical physics outright. Instead, there was a growing collection of edge cases where its predictions failed. Each case could be treated as a special problem, but together they formed a pattern that could not be ignored. Nature was signaling that the classical picture, while powerful, was incomplete. Another source of discomfort was the role of measurement itself. Classical physics assumed that measurements revealed properties that systems already possessed. Observation did not disturb reality, it merely recorded it. But as experiments became more refined, it became increasingly clear that the act of measurement could not be cleanly separated from the phenomena being measured. This idea challenged a cornerstone of classical objectivity. The crisis also exposed tensions between different branches of physics. Mechanics, electromagnetism, and thermodynamics had developed with relative independence, each with its own assumptions and methods. Classical physics had unified them conceptually, but the anomalies suggested that this unity might be superficial. Certain laws worked in one domain but failed in another. The promise of a single, coherent framework began to look fragile. Importantly, the crisis was not resolved by consensus or gradual adjustment. It created a generational divide. Younger physicists were more willing to question foundational assumptions, partly because they were less invested in them. Older physicists, whose careers had been built on classical theory, were understandably reluctant to accept its limitations. This divide was not merely about age, but about philosophical temperament. Those inclined toward realism and determinism struggled more with the implications of the anomalies. Those more comfortable with pragmatism found it easier to accept theories that worked without fully explaining why. This philosophical divergence shaped how different scientists responded to the same evidence. The crisis of classical physics was therefore also a crisis of scientific philosophy. As the pressure mounted, it became clear that no amount of refinement within the classical framework would resolve the contradictions. The problem was not insufficient mathematics or imprecise experiments, it was the framework itself. Concepts like continuity, determinism, and universality were being pushed beyond their domain of validity. Yet even at this stage, few could imagine the nature of the solution. The idea that energy or matter might be quantized was not an obvious next step. It contradicted centuries of thought and clashed with deeply held intuitions. The crisis did not point clearly toward quantum theory, it pointed toward the inadequacy of existing ideas. What would replace them was still unknown. This uncertainty made the period intellectually exhausting. Physicists were working without a clear sense of direction, aware that something fundamental was wrong, but unsure how to fix it. Progress continued, but it was fragmented and uneasy. Each advance seemed to deepen the mystery rather than resolve it. The crisis also forced a re-evaluation of what it meant for a theory to be true. If classical physics was extraordinarily accurate in some domains, but fundamentally wrong in others, how should it be understood? Was it false, or merely limited? Could a theory be both true and incomplete? These questions had no easy answers, but they reshaped scientific thinking. In hindsight, it is tempting to view the crisis of classical physics as an inevitable prelude to quantum theory. But for those living through it, there was nothing inevitable about the outcome. There was only uncertainty, frustration, and a growing sense that physics stood at a crossroads. The familiar path was no longer sufficient, but the new path had not yet been revealed. This is why the crisis of classical physics deserves to be understood not as a failure, but as a necessary moment of transformation. It exposed the limits of a worldview that had dominated science for centuries. It revealed that success in one domain does not guarantee universal validity, and it created the conditions in which a radically new way of thinking could emerge. Without this crisis, there would have been no need to question continuity, determinism, or classical causality. Without sustained experimental resistance, there would have been no justification for radical ideas. The crisis forced physics to confront its own assumptions and, in doing so, opened the door to a deeper and more subtle understanding of nature. In the end, the crisis of classical physics was not resolved by abandoning classical laws entirely, but by recognizing their scope and limitations. Classical physics remained true within its domain, but it could no longer claim to be the final word on reality. This realization was painful, slow, and deeply unsettling. But it was also the necessary precondition for one of the greatest intellectual revolutions in human history. Max Planck's inner conflict did not begin when he introduced the quantum hypothesis. It began much earlier, at the point where his philosophical convictions met the unforgiving demands of experimental reality. He was not a man torn between faith and science, but between two visions of science itself. On one side stood his deep belief in absolute, eternal laws governing nature. On the other stood the growing realization that the phenomena he studied refused to obey those laws in the way classical physics demanded. This tension shaped his intellectual life long before it reshaped physics. Planck entered science with a conviction that was unusual even in his time. He believed that the laws of nature were not provisional constructs, but objective truths that existed independently of human observers. To him, physics was not a creative enterprise in which theories were invented and discarded. It was a disciplined search for principles that were already there. This belief gave his work a philosophical gravity. It also made contradiction deeply troubling. If the universe was rational and lawful, then inconsistencies were not merely technical errors, they were signs that something essential was being misunderstood. This worldview explains why Planck gravitated toward theoretical physics rather than experimental work. He was less interested in manipulating apparatus than in uncovering the conceptual structure behind physical phenomena. Theory, for him, was a bridge between mathematics and reality, a way of expressing universal truths with precision. But this same orientation made him especially sensitive to the cracks that began to appear in classical explanations. When Planck turned his attention to thermodynamics and radiation, he did so with the expectation that classical physics, properly applied, would yield clear and consistent results. Instead, he encountered resistance at every step. Experimental data on blackbody radiation did not align with predictions derived from classical assumptions. At first, he treated this mismatch as a challenge to be overcome within the existing framework. He did not doubt the framework itself, he doubted his ability to apply it correctly. This response reveals the depth of his inner conflict. He trusted the principles of classical physics almost instinctively. They were not just tools, They were expressions of how he believed nature must behave. When equations failed, his first instinct was not to question continuity or determinism, but to search for errors, missing terms, or overlooked assumptions. This prolonged struggle was not stubbornness. It was loyalty to a worldview that had proven its worth over centuries. As months turned into years, the conflict intensified. The data grew clearer, more precise, and more resistant to classical explanation. Each refinement of experiment reduced the space in which classical physics could hide. Planck found himself trapped between two equally compelling obligations: the obligation to respect empirical evidence and the obligation to preserve conceptual coherence. Neither could be sacrificed lightly. What made this conflict especially painful was that Planck understood exactly what was at stake. He was not naively clinging to old ideas out of habit. He knew that abandoning continuity or determinism would have profound consequences for the meaning of physical law. Continuity was not just a mathematical convenience, it was the foundation of causal explanation. Determinism was not just a technical assumption, it was the guarantee that nature was intelligible in principle. To give up either felt like giving up the promise of physics itself. This is why Planck later described his introduction of energy quanta as an act of desperation. The word was not rhetorical. It captured the psychological reality of a man who felt cornered by facts. He did not arrive at quantization through philosophical enthusiasm or creative speculation. He arrived there because every other path had closed. Even then, the inner conflict did not resolve itself. When Planck proposed that energy could be emitted or absorbed only in discrete units, he did not interpret this as a literal description of reality. He treated it as a formal assumption, a mathematical device introduced to make the equations work. In his mind, it was a provisional step, not a metaphysical commitment. He hoped, perhaps even expected, that a deeper classical explanation would eventually emerge, restoring continuity beneath the surface. This cautious attitude reveals how deeply divided he remained. On paper, he had introduced a radical idea. Internally, he resisted its implications. He continued to believe that nature, at its core, was continuous and deterministic. The quantum hypothesis, in his view, was a temporary bridge over a gap in understanding, not the foundation of a new worldview. The conflict between these positions shaped how Planck reacted to the work of younger physicists. When others began to treat quantization as a fundamental feature of nature, he supported their mathematical developments but remained philosophically uneasy. He encouraged research, defended empirical success, and accepted the necessity of new methods. But he did not embrace the idea that randomness or discontinuity might be intrinsic to reality. This hesitation is often misinterpreted as conservatism or lack of imagination. In truth, it reflected the seriousness with which he took the philosophical meaning of science. For Planck, ideas were not interchangeable. They carried implications for how reality was understood and how human reason related to nature. Accepting quantization as fundamental meant accepting that the universe did not conform to the principles he had devoted his life to understanding. The inner conflict also had a moral dimension. Planck believed that scientists had a responsibility to truth that extended beyond personal preference or intellectual fashion. He did not want to misrepresent reality, even unintentionally. Introducing an assumption he did not fully believe in felt like a violation of that responsibility. Yet refusing to introduce it would have meant ignoring overwhelming evidence. This ethical tension intensified the psychological burden he carried. Throughout this period, Planck maintained an extraordinary level of intellectual discipline. He did not dramatize his struggle publicly or frame it as a personal crisis. Instead, he allowed the tension to exist quietly, expressed only in careful language and measured conclusions. This restraint is characteristic of his approach to science. He did not seek recognition as a revolutionary, he sought accuracy. The conflict between philosophy and experiment did not end with the acceptance of the quantum hypothesis. It persisted throughout his life. Even as quantum theory expanded and proved extraordinarily successful, Planck continued to believe that it was incomplete. He hoped for a future synthesis that would reconcile quantization with deeper deterministic principles. This hope was not fulfilled in the way he imagined, but it guided his attitude toward the evolving field. Understanding this inner conflict is essential to understanding why Planck occupies such a unique position in the history of physics. He was both the originator of a revolution and one of its most reluctant participants. He opened the door to quantum theory not because he wished to change the foundations of physics, but because he refused to ignore what nature was telling him. In this sense, his conflict was not a weakness, but a strength. It forced him to move carefully, to justify every step, and to remain aware of the broader implications of his work. It prevented him from treating new ideas as mere intellectual games. Every concept carried weight, and every assumption demanded scrutiny. The story of this inner conflict reveals something profound about the nature of scientific progress. Revolutions are often driven not by those who desire change, but by those who are most committed to existing principles and therefore most deeply troubled when those principles fail. Planck did not seek to overthrow classical physics. He sought to save it. In doing so, he discovered that saving it required transforming it. His struggle stands as a reminder that science is not only a technical activity, but a human one. It involves belief, doubt, loyalty, and courage. The third keynote, Max Planck's inner conflict between philosophy and experiment, is the emotional and intellectual crucible in which quantum theory was forged. Without that conflict, the quantum idea might never have emerged with such clarity, seriousness, and enduring impact. The inner conflict that defined Max Planck's intellectual life did not fade after the quantum hypothesis entered the scientific conversation. Instead, it deepened and matured into a lifelong tension that shaped how he interpreted both his own work and the future of physics. What makes this conflict historically significant is not simply that he experienced doubt, but that he fully understood the philosophical consequences of the path he had opened, and yet could not walk it with ease. His struggle was not with mathematics or experiment, but with meaning. Once the quantum idea proved successful in explaining radiation data, the external pressure eased, but the internal pressure intensified. The equations worked, and that fact could not be denied. Yet success brought a new problem. How should this success be understood? For Planck, accepting a formula was not the same as accepting a worldview. He distinguished sharply between empirical adequacy and ontological commitment. A theory could predict correctly and still fail to describe reality as it truly was. This distinction placed him in an increasingly isolated position as quantum theory developed. Younger physicists were less burdened by classical philosophical commitments and more willing to accept discontinuity and probability as fundamental. They approached the quantum hypothesis not as a temporary device, but as a window into the true structure of nature. Planck watched this development with a mixture of pride and unease. He recognized the power of the new theory, but he remained unconvinced that it represented the final truth. His unease stemmed from a deep concern about the role of causality. Classical physics had offered a universe in which events followed one another according to strict necessity. This picture supported the idea that the world was intelligible in principle, even if human knowledge was limited in practice. Quantum theory, as it evolved, appeared to undermine this guarantee. Probability was no longer merely a reflection of ignorance, it seemed to be woven into the fabric of reality itself. For Planck, this implication was profoundly troubling. If events occurred without sufficient cause, what did that mean for the rational structure of nature? Could science still claim to uncover objective laws, or was it reduced to managing probabilities without deeper explanation? These were not abstract questions for him. They struck at the foundation of why he had chosen science as a vocation in the first place. Yet despite his discomfort, he did not attempt to reverse the course of physics. He did not suppress new ideas or discourage their development. On the contrary, he actively supported younger researchers, defended their right to explore radical interpretations, and used his authority to legitimize emerging work. This behavior reveals an important nuance in his character. His resistance was philosophical, not institutional. He questioned meanings, not methods. This dual stance, supportive in practice, skeptical in interpretation, was the hallmark of his later career. He accepted that quantization was necessary and real at the level of calculation. What he resisted was the claim that indeterminacy represented the final word on nature. He believed, or at least hoped, that a deeper theory might eventually reconcile quantum results with deterministic principles, restoring coherence at a more fundamental level. This hope was not grounded in evidence, but in philosophical conviction. It reflected his belief that reality must ultimately be rational in a way that human reason could grasp. Even as experiments suggested limits to prediction, he held on to the idea that these limits might reflect current ignorance rather than intrinsic randomness. This position placed him at odds with some of the most influential interpretations of quantum mechanics that emerged later. The inner conflict also influenced how he understood scientific explanation. For Planck, explanation meant more than mathematical consistency. It meant conceptual clarity and philosophical satisfaction. A theory that worked but could not be interpreted coherently was, in his view, incomplete. This standard was higher than what many were willing to demand, especially as quantum theory demonstrated its extraordinary predictive power. As the quantum framework expanded to explain atomic structure, chemical behavior, and solid-state phenomena, the pressure to accept its philosophical implications grew stronger. The theory was no longer confined to a single problem, it was reshaping entire fields. Each success made it harder to maintain the hope that quantization was merely a surface feature masking a deeper classical reality. Yet Planck did not abandon that hope. He continued to argue that science should not confuse practical success with ultimate understanding. He warned against mistaking mathematical formalism for physical insight. These warnings were not reactionary, they were consistent with his lifelong commitment to intellectual rigor. He believed that science advanced not only by accumulating results, but by reflecting critically on their meaning. This reflective stance often left him standing apart from the excitement of the quantum revolution. While others celebrated the overthrow of classical concepts, he remained sober and cautious. He understood that revolutions bring clarity in some areas and confusion in others. What was gained in predictive power might be lost in conceptual transparency. This trade-off concerned him deeply. The emotional cost of this position should not be underestimated. To be recognized as the originator of a new era, while feeling unable to fully endorse its philosophical foundations, is a lonely place to stand. Planck lived long enough to see quantum theory flourish far beyond its initial scope. He witnessed the rise of interpretations that treated uncertainty and probability as fundamental, not provisional. Each development reinforced the distance between his original intentions and the trajectory of the field. Despite this distance, he never disowned his contribution. He accepted responsibility for introducing the quantum hypothesis and acknowledged its necessity. His conflict was not with what he had done, but with what it seemed to imply. This distinction reveals the integrity of his intellectual character. He did not rewrite his past to align with the present. He allowed the tension to remain visible. The conflict between philosophy and experiment also shaped his broader reflections on science and society. He became increasingly concerned about the limits of scientific knowledge and the dangers of overconfidence. He cautioned against turning theories into dogmas and reminded audiences that science, however powerful, operates within conceptual boundaries. These reflections were informed by his own experience of seeing cherished principles challenged by evidence. In this way, his inner conflict matured into wisdom. He came to see uncertainty not only as a technical feature of quantum mechanics, but as a reminder of the humility required in the pursuit of knowledge. While he never fully embraced indeterminism, he recognized that science must remain open to revision at its deepest levels. This recognition did not resolve his philosophical discomfort, but it softened it. Understanding this part of his story allows us to see the quantum revolution in a more human light. It was not driven solely by bold speculation or youthful rebellion. It was also shaped by the quiet struggle of a thinker who took ideas seriously and understood their consequences. Planck's reluctance was not a flaw, it was evidence of how much was at stake. The third keynote, when fully explored, reveals that quantum theory was born not only from experimental necessity, but from an internal struggle between two visions of reality. One vision promised continuity, determinism, and complete intelligibility. The other emerged reluctantly from data that refused to conform. Planck stood at the intersection of these visions, unable to fully abandon either. His legacy, therefore, is not just that of a founder, but of a witness. He witnessed the moment when classical certainty gave way to quantum ambiguity. He did not celebrate that moment uncritically, nor did he reject it. He lived within its tension, and in doing so, he showed that the deepest scientific advances are often accompanied by profound philosophical costs. This unresolved conflict is not a historical curiosity, it remains relevant today. Modern physics still grapples with questions about determinism, realism, and the nature of explanation. The discomfort Planck felt has not disappeared, it has been inherited. His inner struggle reminds us that progress in knowledge does not always bring comfort, and that understanding the universe may require accepting limits to the very principles that once made it feel fully intelligible. The birth of the quantum idea did not arrive as a triumphant breakthrough announced with confidence and clarity. It emerged quietly, almost reluctantly, from a problem that refused to disappear. At the center of this moment stood Max Planck, a man who did not set out to change physics, but who found himself forced to do so by the stubborn honesty of nature. The problem that led to this turning point was deceptively simple. How does heated matter emit radiation? Experiments had shown with great precision how the intensity of radiation depended on frequency and temperature. The data were reliable, repeatable, and increasingly refined. Classical physics, however, could not reproduce these results without leading to absurd predictions. Theoretical curves diverged sharply from experimental ones, especially at high frequencies, where classical laws implied an infinite release of energy. Planck approached this problem with the mindset of a conservative theorist. His goal was not to invent a new picture of reality, but to derive an equation that matched the data while remaining faithful to established principles. For years, he worked within the classical framework, adjusting assumptions and refining calculations. Each attempt failed in a different way. The experiments did not bend. Faced with this impasse, Planck made a move that would later be recognized as revolutionary, though he himself did not see it that way at the time. He introduced a new assumption about the exchange of energy between matter and radiation. Instead of being continuous, energy could only be emitted or absorbed in discrete portions, proportional to the frequency of the radiation. This proportionality involved a new constant, a number that would later become fundamental to physics. What is crucial to understand is the spirit in which this assumption was made. Planck did not believe that energy was literally quantized in this way. He treated the assumption as a formal device, a mathematical hypothesis introduced to make the equations fit the experimental data. In his own words, it was an act of desperation, not conviction. He was willing to sacrifice conceptual comfort to preserve agreement with observation. Yet this single assumption achieved what years of classical reasoning could not. The resulting formula matched experimental measurements with astonishing accuracy across all frequencies. The agreement was not approximate or partial, it was exact. For the first time, theory and experiment aligned perfectly in the description of blackbody radiation. This success marked the true birth of the quantum idea, not because Planck announced a new worldview, but because he crossed a conceptual boundary that could not be uncrossed. By introducing discreteness into energy exchange, he violated one of the deepest assumptions of classical physics: continuity. long regarded as a fundamental feature of nature, had been broken. At first, the significance of this break was not widely recognized. Many physicists viewed Planck's formula as an empirical success without philosophical consequence. Some assumed that a deeper classical explanation would eventually justify the result without requiring genuine quantization. Planck himself shared this hope. He did not yet see his assumption as a statement about reality, but as a provisional step. The quantum idea, in its infancy, was therefore fragile and ambiguous. It existed as a mathematical rule without a clear physical interpretation. This ambiguity allowed it to be accepted pragmatically while postponing deeper questions. Physicists could use the formula without committing to what it meant. However, the logic of the idea was relentless. If energy exchange occurred in discrete units in one context, why not in others? The constant Planck introduced began to appear in unexpected places, connecting radiation, matter, and microscopic processes. What had seemed like a technical fix started to look like a fundamental feature of nature. The birth of the quantum idea was thus not a single event, but a threshold crossing. Once discreteness entered physics, it changed the questions scientists could ask and the answers they could accept. Even if Planck hoped to retreat to classical continuity, the door he had opened led forward, not backward. This moment also revealed a new relationship between theory and experiment. Classical physics had often guided experiment by predicting what should be observed. In this case, experiment forced theory to adapt in a way that theory itself did not anticipate. The authority shifted. Nature, not philosophy, dictated the terms. Importantly, the quantum idea was born without imagery. There were no intuitive pictures of energy packets moving through space. The concept was abstract, mathematical, and counterintuitive. This lack of visualization contributed to the unease surrounding it. Physics had long relied on mechanical analogies and continuous motion. Quantization resisted such analogies. Yet the power of the idea lay precisely in its abstraction. By abandoning the demand for intuitive continuity, Planck achieved a level of accuracy that classical reasoning could not reach. The success of the quantum hypothesis suggested that nature might not conform to human intuition, even when that intuition was supported by centuries of experience. The birth of the quantum idea therefore represents a shift in how physics related to reality. It marked the beginning of a willingness to accept concepts that worked even when they challenged deeply held beliefs about how the world must behave. This willingness did not arise from enthusiasm for novelty, but from respect for evidence. In hindsight, this moment appears inevitable. In reality, it was precarious. Had Planck refused to introduce his assumption, the crisis might have persisted longer. Had he framed it more boldly, it might have been rejected outright. Its quiet, tentative introduction allowed it to take root. The quantum idea was born not as a declaration of a new era, but as a reluctant concession to experimental truth. Its revolutionary consequences were revealed only gradually, as others explored its implications and extended its reach. But the moment of birth, when energy was first treated as discrete rather than continuous, stands as one of the most profound turning points in the history of science. It shows that revolutions do not always begin with confidence. Sometimes they begin with hesitation, doubt, and a single assumption made against one's deepest instincts. The moment the quantum idea entered physics, it did not trigger celebration or immediate acceptance. Instead, it was met with resistance, doubt, and a profound sense of unease. This reaction was not driven by ignorance or stubbornness, but by the recognition that something deeply unsettling had occurred. The new idea worked, yet it seemed to undermine the conceptual foundations upon which physics had been built for centuries. What followed was not a clean transition from old to new, but a period of tension in which the implications of the quantum hypothesis were simultaneously acknowledged and resisted. At the center of this tension stood Max Planck, whose personal reaction mirrored the broader response of the scientific community. Although his formula matched experimental data perfectly, He did not interpret this success as proof that nature was fundamentally quantized. He regarded the hypothesis as provisional, a formal assumption that solved a specific problem but did not yet justify a wholesale revision of physical reality. This cautious stance set the tone for how the idea was initially received. Many physicists shared this caution. Classical physics had earned immense trust through centuries of success. Its principles were not arbitrary, they were woven into the intellectual fabric of science. Continuity, determinism, and causality were not merely technical assumptions, but pillars of rational explanation. The suggestion that energy might behave discontinuously felt less like progress and more like a threat to intelligibility itself. Resistance, therefore, took subtle forms. Rather than rejecting the quantum hypothesis outright, many scientists treated it as a calculational trick. They used the formulas where they worked and avoided asking what they meant. This pragmatic approach allowed research to continue without forcing immediate philosophical confrontation. It was a way of postponing the deeper implications while benefiting from the empirical success. Doubt persisted because the quantum idea lacked intuitive grounding. Classical physics had always offered mental pictures, particles moving along trajectories, waves spreading smoothly through space, causes leading predictably to effects. Quantization offered none of this. It introduced discrete jumps without providing a mechanism that could be visualized or explained in familiar terms. For many, this absence of imagery signaled incompleteness rather than truth. Even those who extended the quantum idea into new domains did so cautiously. Each successful application strengthened the theory's practical value while intensifying discomfort about its meaning. The more problems it solved, the harder it became to dismiss it as a temporary fix. Yet acceptance lagged behind success, because acceptance required abandoning deeply held beliefs about how nature ought to behave. This gap between effectiveness and understanding created a strange intellectual atmosphere. Physics advanced rapidly, but confidence in its conceptual foundations weakened. Scientists could calculate results with unprecedented accuracy, yet struggled to explain what those calculations said about reality. The quantum idea seemed to demand obedience rather than comprehension. Ironically, the revolution was unfolding even as many resisted acknowledging it. The constant introduced by Planck began appearing across different phenomena, linking radiation, matter, and microscopic processes. Each appearance reinforced the idea that quantization was not an isolated anomaly, but a unifying principle. What had been intended as a narrow solution was quietly becoming a cornerstone. The unintended nature of this revolution is one of its most striking features. Planck did not aim to overturn classical physics, and neither did many who followed him. They sought solutions to specific problems, not a new worldview. Yet each solution chipped away at classical assumptions, eroding them from within rather than attacking them directly. This incremental erosion made resistance psychologically easier but philosophically more dangerous. By the time it became clear that classical continuity could not be fully restored, the transformation was already well underway. Physics had crossed a threshold without fully acknowledging it. Doubt also persisted because quantum theory seemed to introduce limits to knowledge itself. Probabilistic outcomes and discrete transitions suggested that prediction might be inherently constrained. For scientists trained to believe in complete predictability given sufficient information, this implication was deeply unsettling. It raised questions not only about physics, but about the scope of human reason. Some hoped that the resistance would prove temporary, that a deeper theory would emerge to reconcile quantization with classical determinism. This hope allowed skepticism to coexist with progress. One could accept quantum results while believing they were incomplete. This belief sustained many through the transition, even as evidence mounted that the new framework was here to stay. What makes this period historically significant is that resistance did not stop the revolution, it shaped it. Because acceptance was cautious, the theory developed with extraordinary rigor. Every assumption was scrutinized, every implication debated. The discomfort forced clarity, even if it delayed consensus. The unintended revolution also changed how science understood itself. It revealed that theoretical success does not guarantee philosophical comfort, and that nature may not conform to human expectations of order and simplicity. This realization marked a shift from confidence in intuition to reliance on formal structures, even when those structures resisted interpretation. In the end, resistance and doubt did not weaken the quantum idea, they strengthened it. By surviving skepticism, it demonstrated resilience. By provoking discomfort, it exposed the limits of classical thinking. And by advancing without intention to revolutionize, it showed that the most profound transformations in science often arise not from bold declarations, but from reluctant concessions to evidence. The fifth keynote captures this paradox. Quantum theory did not announce itself as a revolution, it became one despite resistance, through the quiet accumulation of successes that could not be explained away. Its rise reminds us that scientific change is rarely clean or comfortable. It unfolds through doubt, hesitation, and unintended consequences. And it is precisely this process that gives it depth and endurance. As the quantum idea began to settle into the foundations of physics, one element emerged as its quiet anchor, a single number that transformed an abstract assumption into a new way of seeing the universe. This number, later known as Planck's constant, marked the passage from a technical solution to a conceptual revolution. What had begun as a proportionality factor in an equation slowly revealed itself as a boundary between two worlds, separating the familiar realm of classical experience from a deeper, stranger layer of reality. When Max Planck first introduced this constant, he did not assign it any special philosophical meaning. To him, it was a numerical coefficient required to make theory align with experiment. It had no symbolic role, no claim to universality beyond the specific problem of radiation. Yet physics has a way of revealing significance gradually. As the constant reappeared in different contexts, its importance became impossible to ignore. What made this constant extraordinary was not its size, but what it represented. It set a scale at which classical concepts ceased to apply cleanly. Above this scale, energy appeared continuous, and classical laws worked with remarkable accuracy. Below it, continuity fractured, processes occurred in discrete steps, and classical intuition lost its grip. The constant did not merely adjust equations, it defined a threshold of reality. This realization transformed how physicists understood the relationship between theory and the world. In classical physics, constants like the speed of light or the gravitational constant described properties of nature that fit comfortably within existing frameworks. Planck's constant did something different. It limited what could be known and how it could be known. It implied that nature itself imposed a minimum scale of action, below which traditional descriptions broke down. As the constant spread into new theories, its role expanded. It appeared in explanations of atomic structure, in the behavior of electrons, and in the interaction between light and matter. Each appearance reinforced the idea that quantization was not a local anomaly, but a universal principle. The constant linked phenomena that had once seemed unrelated, revealing a hidden coherence beneath the surface diversity of physical behavior. This coherence, however, came at a cost. The new worldview suggested by the constant was not deterministic in the classical sense. Instead of smooth trajectories and predictable outcomes, physics now dealt with probabilities and discrete transitions. The constant fixed the scale of uncertainty, making it an intrinsic feature of nature rather than a defect of measurement. This was a profound shift in perspective. The transformation from abstract constant to worldview did not happen overnight. For years, the constant was treated as a useful parameter rather than a philosophical statement. Physicists used it because it worked, not because they understood its meaning. Yet over time, it became clear that the constant was not just part of the machinery of quantum theory, it was its foundation. The presence of this constant forced a redefinition of fundamental concepts. Energy, once thought of as infinitely divisible, now came in quanta action, a quantity central to mechanics, was no longer arbitrary but bounded from below. Even the act of measurement was affected, as the constant set limits on how precisely certain pairs of properties could be known simultaneously. This redefinition extended beyond physics into philosophy. The idea that there exists a fundamental limit to knowledge challenged centuries of thought about determinism and objectivity. The constant suggested that the universe was not simply unknown in parts, but unknowable in principle beyond certain boundaries. Reality itself seemed to resist complete description. What makes this development especially striking is that it emerged without intent. Planck did not set out to redefine reality. He introduced a constant to solve a problem. The worldview that followed was constructed by others, step by step, as they explored the implications of that number. The revolution was not declared, it unfolded. The constant also changed how scientists understood explanation. Classical physics aimed to reduce complexity by tracing phenomena back to simpler, more fundamental processes. Quantum physics, constrained by Planck's constant, accepted irreducible limits. Explanation no longer meant full prediction, but statistical description within fixed boundaries. This shift altered the goals of theory itself. Despite its abstract nature, the constant had concrete consequences. It shaped the development of technologies that relied on quantum principles, from electronics to modern communication systems. The same number that limited knowledge also enabled new forms of control and precision. This dual role underscored the paradox at the heart of the quantum worldview. From a broader perspective, the emergence of this constant marked a turning point in humanity's understanding of nature. It signaled the end of the assumption that the universe could be fully described using concepts drawn from everyday experience. In its place arose a framework that was mathematically precise but conceptually challenging, powerful but unsettling. The sixth keynote captures this transition. It is the moment when quantum theory ceased to be a collection of technical fixes and became a lens through which reality itself was interpreted. The constant introduced by Planck did more than solve an equation. It redefined the scale at which nature operates and the limits within which human reason must work. In the end, the journey from abstract constant to new worldview illustrates how scientific revolutions often proceed. They begin with modest steps, guided by necessity rather than ambition. Only later do their full implications become visible. The constant that once seemed like a minor adjustment became a cornerstone of modern physics, reshaping not only equations, but the very idea of what it means to understand the universe. The lasting legacy of quantum thinking is not confined to equations, laboratories, or technological devices. It is woven into the modern understanding of reality itself. What began as a reluctant adjustment to explain experimental data evolved into a framework that reshaped science, philosophy, and humanity's sense of its place in the universe. This legacy is inseparable from the figure of Max Planck, not because he intended to create it, but because his commitment to truth over comfort opened a path that could not be closed. One of the most enduring consequences of quantum thinking is the recognition that classical certainty has limits. Before the quantum revolution, it was widely believed that nature could, in principle, be fully predicted if enough information were available. Quantum theory challenged this assumption at its core. It introduced the idea that uncertainty is not merely a practical limitation, but a fundamental feature of the world. This shift altered the goals of science. Instead of seeking perfect prediction, physics learned to work within probabilistic boundaries, redefining what it means to explain a phenomenon. This redefinition extended far beyond physics. Philosophy, long concerned with questions of determinism, causality, and knowledge, was forced to engage with a universe that did not conform to classical expectations. The idea that reality might not possess definite properties independent of observation challenged traditional notions of objectivity. While interpretations differ, the influence of quantum thinking on philosophical debates about realism and knowledge remains profound and unresolved. In practical terms, the legacy of quantum theory is visible everywhere. technologies that define modern life, semiconductors, lasers, medical imaging, and digital communication, are built on principles that would be impossible without quantization. These applications demonstrate a striking paradox: a theory that limits what can be known also enables unprecedented control over matter and energy. The same framework that undermines classical intuition empowers modern engineering. Yet the legacy is not merely technological. Quantum thinking introduced a new scientific attitude toward nature. It taught physicists to trust formal structures even when intuition fails. This shift marked a departure from centuries of reliance on mechanical analogies and visualizable models. Mathematics became not just a tool, but the primary language through which reality was accessed. Understanding no longer required picturing processes in familiar terms, it required accepting abstract relationships as fundamental. This change in attitude influenced subsequent scientific revolutions. Fields such as particle physics and cosmology inherited the quantum lesson that reality may operate according to principles that defy everyday experience. The willingness to accept counterintuitive ideas, once resisted, became a hallmark of advanced theoretical work. In this sense, quantum thinking reshaped not only what scientists believed, but how they approached belief itself. The legacy also includes an enduring tension. Quantum theory works extraordinarily well, yet its interpretation remains contested. Questions about what the theory says about reality, measurement, and causality continue to provoke debate. This unresolved state is not a failure. It is a reflection of the depth of the transformation quantum thinking initiated. It revealed that understanding nature may involve permanent conceptual challenges, not final answers. For Planck himself, this legacy was deeply ambivalent. He lived to see quantum theory expand far beyond its origins, becoming central to modern physics. He witnessed its triumphs and its philosophical controversies. Yet he never fully reconciled the new worldview with his original belief in absolute determinism. His position embodies an important aspect of the legacy: the recognition that scientific progress can outpace philosophical comfort. This tension is itself instructive. It reminds us that revolutions in knowledge do not erase previous ways of thinking, they coexist with them, often uneasily. Classical physics did not disappear, it found its domain of validity. Quantum theory did not negate classical truth, it revealed its limits. The legacy is therefore not replacement, but layering, a more nuanced picture of reality built upon, rather than entirely discarding what came before. Another lasting impact of quantum thinking is its influence on how uncertainty is valued. In earlier scientific traditions, uncertainty was something to be eliminated. In the quantum framework, uncertainty became a guide, pointing toward fundamental structure. This shift has broader cultural implications. It encourages humility in the face of complexity and cautions against claims of complete knowledge. In an age driven by data and prediction, this lesson remains relevant. The human dimension of this legacy is equally important. The story of quantum theory illustrates that transformative ideas often arise from individuals who do not seek transformation. Planck's contribution was not driven by a desire to revolutionize science, but by fidelity to evidence. This model of intellectual integrity has enduring significance. It shows that progress depends not only on creativity, but on the courage to follow results wherever they lead. Quantum thinking also altered the relationship between observer and observed. In classical physics, the observer stood outside the system, recording its behavior without influencing it. Quantum theory blurred this boundary, suggesting that observation plays an active role in defining outcomes. This idea has influenced discussions far beyond physics, touching psychology, philosophy of mind, and even cultural interpretations of reality. Whether taken literally or metaphorically, it underscores the interconnectedness of knowledge and perspective. Perhaps the most profound aspect of the legacy is the way quantum theory changed humanity's image of the universe. The clockwork cosmos of classical physics gave way to a world that is subtle, layered, and resistant to complete description. This new image is neither chaotic nor irrational, but governed by laws that operate differently from everyday expectations. It invites wonder without offering full transparency. In this sense, quantum thinking restored a sense of mystery to science without abandoning rigor. It showed that mystery and precision are not opposites. One can calculate with extraordinary accuracy while accepting that the underlying reality defies simple explanation. This balance between knowledge and mystery is a defining feature of modern science. The seventh keynote, when fully understood, reveals that the true legacy of quantum theory lies not in any single discovery, but in a transformed relationship between humans and nature. It taught us that reality is deeper than intuition, that certainty has limits, and that truth sometimes requires abandoning the comfort of familiar ideas. It also demonstrated that such abandonment, though painful, can open pathways to understanding that were previously unimaginable. Quantum thinking continues to shape the future, not because all its questions are answered, but because it changed the kinds of questions we are willing to ask. That is its enduring legacy, a science that is more powerful, more humble, and more aware of the profound complexity of the universe it seeks to understand.